A very good morning to all of you. We will go to the third and final part of. In the last lecture, which was lecture 2, we looked at some basic principles of laser action, energy level diagrams, and then we looked at of course Einstein's coefficient and how they lead to efficient laser action from different energy level systems. Then we also looked at a video, an animation which showed the role of the cavity. That's what we did in the last class. An important note, please note that I have made some modifications in the last PPT. So what you see as course material for lecture 2 is little bit modified to make it easier for you. Whatever was covered, I have put in a slightly different manner so that it is easier for you. So when you refer to that, please refer to the modified version which is available right now in the web. These are the things which we looked at in lecture 2, and in lecture 3 we look at the principles of some very specific, most commonly used laser systems. Some of them are old and traditional, some of them new. We explain it on the basis of energy level diagrams and how population inversion is achieved in these systems. What are the systems used? What is the kind of laser? What are the main features? Then we also look at laser as a very powerful tool for various kind of applications. We survey a few new developments in laser with a little bit of historical perspective, and then we close. That's the plan of this lecture. As I mentioned yesterday, that in the last class, the purpose is not give a lot of content. Content is available everywhere, but the concepts, learning which you can appreciate the content and understand the content properly. Of course, a lot of content is also there, but the stress and emphasis is on the concept and to put things in perspective. We will proceed by looking at the laser cavity. The lasing medium, so far we were talking about the absorption process, emission process, etc. in the lasing medium. This medium is kept inside a cavity. The laser cavity basically consists of a medium and two end mirrors. I have touched upon this in the last lecture. I am just repeating a part of it. There will be spontaneous emissions to start with, events of spontaneous emission. Then one of those photons will start, it will trigger a stimulated emission process. Remember, stimulated emission happens when there is a field. There is already a field, exciting field. What you get out of stimulated emission will be another photon along with the original photon which stimulated it, both of them coherent, in phase, exactly in the same direction and of the same wavelength and frequency. This meets other excited atoms in the cavity, and this process continues. In the next interaction, if these two photons interact with two atoms, you have 4 beams coming out totally, 2 of the original ones and 2 newly generated stimulated ones. This travels through the medium. The question is, will it all be absorbed by the medium or will it trigger stimulated emission? The answer to that is, it depends whether there are larger number of atoms in the ground state or larger number in the excited state. If it is larger number in the ground state, then most of the photons will be absorbed. On the other hand, if they are already in the excited state, the stimulated emission process which we are discussing so far will happen, and you get the laser photons coming out of it in the same direction, same frequency, and with coherence and phase relation. That is what we want out of the cavity. So the cavity has to be filled with a population inverted medium, which means a medium in which there is considerably larger number in the excited state rather than the ground state. How do we do this? That is what we discussed in the last class, the various tricks using energy level diagrams. And that is why we can't have lasers with any material, only very specific systems like helium ion, etc. we are going to see. Only they permit this kind of energy level structure. Look at the laser cavity. The laser cavity is basically something which hosts this medium, and it provides the gain. It hosts the population inverted medium. So the first event is triggered by a stimulated emission. This first stimulated emission event is triggered by a spontaneous emission, and that triggers further events of stimulated emission. And if you have a population inversion, as photons travel from one end through the medium, it will gain in intensity, larger and larger number of photons as I have shown in the last class. Now we put a mirror at the other end, and this will get reflected back. Thus it gets reflected back and forth. What happens when it's reflected back? The photons go through the inverted medium once again, and there is again this population inverted medium. So there are more and more events of stimulated emission, and you get a very large number of photons going to the second mirror. This continues. That is what happens in a cavity. So the cavity will have losses and gains. Why should a cavity have loss? We have just now discussed gain. By gain, I mean there should be a large number of photons coming out. But the cavity is a physical entity. The medium, though we have population inversion, there are some photons which will absorb it. The walls of the cavity will absorb it. The reflection will not be 100%. Reflection will be less than that. So there is some loss. Light will be scattered by the various parts of the cavity. All that leads to a loss. Let us look at the cavity in a little greater detail. We have the cavity here. You have the end mirrors. This is just a schematic. A spontaneous emission event which will happen automatically will trigger a stimulated emission event. So you have two photons after this stimulated emission. One initial one and the one which is caused by this. So let us have a clearer and bigger picture here. Mirror 1, mirror 2, the gain medium is available here, which means there is the population inversion. So the first stimulated emission photon meets two atoms, meets one atom, and the original and the stimulated both travel in this direction. This meets one atom, this meets one atom, like that. Now each one of them is going to meet okay, and this is happening in a fraction of a millimeter. That depends on your density, how many atoms you have kept there and how many of them are inverted in population. So we have a very large number here, tens of thousands photons here. Then the mirror sends all of them back into the medium. They come back and again meet atoms, and the basic process of stimulated emission happens. The basic process of stimulated emission is this. A photon interacts with an excited atom and gives another photon. These photons 1 and 2 together travel. That's what is happening here. I am explaining what is happening there. So this is a zoom of whatever is happening here. Okay, so we have the cavity, we have a large number on this side. All of them are sent back by the cavity and they travel here, and huge, the number becomes very huge when it comes here. Then there is another mirror here which sends it back, and on the way back again they will meet atoms depending upon how many atoms you keep here. Of course Avogadro number is a very large number, you have a very large number of atoms here. So in the process you have a build up of energy. Light energy is built up at a particular frequency corresponding to the energy levels. Now comes the trick. You have one mirror 100% reflection, the other one will be 99.99, depending upon different lasers it will be 999 or whatever it is, 99 and all that. So because of that small difference the laser comes out. This is what you have seen in the animation also, which I showed in the last class. So what is the role of the cavity? The cavity holds the medium, the gain medium, hosts the gain medium with a population inversion. That is one important thing. And the other important role of the cavity is the cavity will select the modes. What do you mean select the modes? The cavity, the distance between the mirrors determine which wavelength is going to come out. This is called mode selection. That leads to monochromaticity. A highly monochromatic beam only will come from a given cavity. If you want if you want to tune the frequency, you have to adjust the mirror distance between the mirrors. And a very important thing, what makes the laser fantastic is the directionality, extreme directionality, very narrow angle of divergence. It goes almost like a straight line for several kilometers distance without spread. For example, a torchlight, if you take a torchlight, the torchlight will spread to a very large area within a few meters and energy will be lost. In the sense it will be made very, the intensity becomes very low as far as zero, nearly zero. In the case of a laser, it is highly directional. How does this directionality come in? That is caused by the cavity. Look at the cavity once again. Suppose there is a photon traveling like that. It gets reflected. Suppose there is a photon traveling at a small angle from the horizontal at this. That gets reflected according to the laws of reflection. It doesn't come back exactly, it gets reflected away. So you see that even if very small angle, even if it is at a slightly different angle from the horizontal, eventually it will be lost. And what you get will be whatever is exactly directional. That is the secret of the directionality of the laser. Once again, if a photon travels like this to the mirror, exactly horizontal, perpendicular, exactly perpendicular to the mirror, horizontal is not important, exactly perpendicular to the mirror, it will come back exactly in this direction. Any photon which travels at a little angle will get reflected like this, I equal to R, law of reflection. And after a few reflections, it will not reach the other mirror, it will be lost. Which means what all you get, still there is enough large number to get. What all you get will be extremely linear, extremely along directional. That is why it is highly directional. This is the role of the cavity in the laser. Okay, now there is loss and there is gain. There is loss because of various reasons which I mentioned. Also some absorption will take place. That is given by the coefficient alpha here. And the gain is denoted by G. This is another way of expressing this, what I am saying qualitatively here. What I am saying is, or what this equation means is the following. There is a medium with absorption alpha and gain G. The mirror reflectivities are R1 and R2 and L is the length of the laser cavity where the active medium is kept. Loss mechanisms I already mentioned, I have written here the loss mechanisms. The gain is from the stimulated emission, population inversion. So if you want to get laser out of it, there must be enough number of photons and that number should be larger than the number of photons lost by the various loss mechanisms, or gain is more than the loss. If you satisfy that condition, then you will get the laser action. This is called the gain condition. I have just given an introduction to what is meant by the gain condition or threshold condition in minutes. If the number of photons, suppose you have kept only very few atoms there, so only very few events of stimulated emission, then you will not get enough number of photons. That is what is meant by the threshold condition. It should be larger than a particular number so that, and quantitatively that is given by this. This is the condition, and more details you can see. But this concept, if you go to the books, text, you will be able to look at the threshold condition and understand what it says. it says gain should be more than the loss, and then only we'll get anything out of it. Let us look at some specific laser systems, popular specific laser system. Even this will be available in the textbooks, energy level diagram and all that. I will try to give you the concepts which mostly may not be available in the books and how you approach it and things like that. When you look at a specific laser system, you have to focus on how population inversion is achieved in that. How the energy level scheme favors a population inversion. That is one consideration. The other consideration is how it is excited, what is the pumping mechanism. And then comes various other features of that, convenience and various other features of that particular laser system. We will see, on that basis we will evaluate various lasers. And most importantly, what gives this energy levels system? You will see shortly that the different lasers have somewhat different kind of schemes of energy levels. So you are going to see different the different schemes of energy level. So the physics is there, how to get that particular energy level. For example, let us look at ruby laser. Ruby. What is ruby? You know what is ruby? It's just aluminum oxide crystal with some modification. If it is just purely aluminum oxide, it will be very cheap and it will not be much useful. Crystal of aluminum oxide. But a few aluminum atoms or actually ions in the crystal will be replaced by chromium, and then it becomes a new system which is called the ruby, and it has all the optical properties, fantastic optical properties of ruby, which aluminum oxide does not have. By this doping, it acquires all that. How does it happen? The physics of it is described by what is called the crystal field theory. The crystal field theory talks about the modifications in energy level schemes in a crystal because of some impurities, some structural modifications, such as a few aluminums in aluminum oxide crystal are replaced by chromium. If you replace by something else, you will get some other color. In fact, like ruby, most of these precious stones arise like that by this crystal field effect. The color and optical properties of this are governed by the crystal field effects, and that is how the physics of this is described. Come back to the ruby laser. The ruby laser, there are a few aspects. As I said, we should look at what kind of laser it is, how convenient or inconvenient it is, and what is the wavelength, and what will be the energy level system. These are the things. So let's first talk about the energy level system. As I mentioned, it is a case where aluminum oxide is modified. Aluminum oxide is transparent. There is no transition which will give you any visible light out of it. But if you modify it and make it into ruby by replacing a few aluminums by chromium, then you have a new set of levels appearing, and these are called crystal field levels, and the origin of that is quantum mechanics. Beyond this, it will be difficult for you to understand about the energy level system. Now let us, the other aspects are, it is optical excitation. The excitation is done by pumping light. Some light is given for the excitation. The rest of it will be clear once you look at the energy level diagram. And of course, the color is red. Have a good look at the system there. One energy level, and then there are a few bands. The bands, the dark bands here, are collections of energy levels. And how it originates is again quantum mechanics. When you do advanced quantum mechanics, you will know how this energy levels become, the atoms interact together. If it is a single atom like a hydrogen atom somewhere in space, then it will have only energy level, sharp energy levels. But if the same hydrogen comes closer, they start interacting with each other. And if you make a hydrogen solid, you will have bands. So individual atoms will have individual energy levels, whereas collection of atoms in the form of a solid will have bands. This is called the band structure of solids, crystals. If it is periodic, you will have a well-defined band structure for a crystal. So in this crystal, which ruby, you have bands corresponding to these energy levels I have shown. So they are given by some names. These names come from crystal field theory. Do not worry about the names. There are two bands here, which you can see now. and these can be excited by slightly different wavelengths. So you could use any one of them for excitation. And once it goes to the, this is now a 3-level system. You remember what we discussed thoroughly about 3-level systems. So there is nothing more to be said. 3-level systems uses a trick. Just to repeat, just between 2 levels you cannot have laser action. For laser action you need stimulated emission, and for that you need population inversion, larger number of atoms in the excited state, which is not the normal case. Normally most of the atoms are in the ground state. So somehow we have to trick the system into having a large number in the excited state. That is the upper laser level. In this case, the ground state is the lower laser level, and these two, take one of them, any one of them. This one is the upper laser level. Okay, so that now how to populate the upper laser level? For that we use a trick. The trick is this: pump into a higher level, which decays very fast, and very fast the atoms, whichever we pump the atoms from the ground state, and that goes here. One of them, consider only one of them, and then that very quickly, 10 power minus 12 seconds, they are all here. They come here. Why do they stay here longer? Because this is something like 10 power minus 8 seconds. So 4 orders of magnitude of time. So for that much huge time, okay, huge means 10 power minus 8 seconds is not huge, but relatively. So we have a larger number of atoms sitting here, and that is what we want, population inversion. Once we have population inversion, we can have the Einstein's new emission, stimulated emission, and that is how this laser comes out. But you are competing with the ground state, as I mentioned in the last class. So there are some issues. It cannot give a continuous laser. It is very difficult to get a continuous laser out of such systems, and it gets heated up because of what are called non-radiative transitions. Some of the transitions which happen in this system are non-radiative, which don't result in irradiation. So that goes as heat, and this laser needs to be cooled. It's a crystal, so the quality will degrade if you don't cool the crystal. And this is ideal for a pulse laser. Okay, once you de-excite this and get the laser action, again you pump it and populate it like that. Now there are 2 levels. You could consider any one of them. Both of them can work. You could either, if you use this particular excitation, it will go here, and this system will work. If you use this pump, the other one will work. So you can get different wavelengths out of it. This is the optical excitation of this. Now the cavity design. The cavity, the cross section of the cavity is elliptical. This is a very interesting point in solid state lasers which we can. This is the cavity which I am talking about, and how to keep the medium here. How to keep the medium here and how to pump it. So you have to first pump it. So you need to have a lamp there to pump it, optical pumping. So you put a very powerful lamp there to do this. And the atoms within 10 power minus 12 seconds, they come here by a non-radiative transition, and this lifetime is 10 power minus 8 seconds. So you have a lamp in the cavity. These are the mirrors. And then we have the ruby rod, the crystal in the form of a rod. This is how it is. So the actual gain medium is here. Now there is an engineering design problem. How do we couple maximum light emitted by this lamp? The lamp is emitting in all directions. How do we couple the maximum light into this? Please note, the purpose of that is to excite, optical excitation. Why have we kept a lamp there? To do this excitation. So the purpose of it is to excite the energy levels in ruby. Any light, for example, which is going this direction, all that is lost. All the light should come here and excite the ruby rod. That's the purpose. Any light, any beam of light which is not doing that is lost. It's a waste. So how do you define it very efficiently? If you put a rod like this, you will see that only these beams are useful, the rest of the light is lost, huge loss. So there is a very clever trick here. We make use of the wonders of mathematics here. We use an elliptical cavity. Doesn't look like an ellipse, but assume that it is an ellipse. This is the cross section of the cavity. I have drawn the cross section of the cavity. So it is looking like that. So the laser rod will be kept like this, the lamp will be kept like this, the laser rod will be kept like this. Okay, so it is kept like that. For clarity, let us draw this again. I have a laser cavity of this kind. The purpose of the lamp is this, to excite ruby, and the purpose of ruby is of course to get this out. Now look at this ellipse. The ellipse has a wonderful property. The ellipse has two foci, two foci, and from this foci, whatever light beam goes and gets reflected from the cavity necessarily comes whichever direction it goes. How do we know that? How do we prove this? This happens according to a rule. This reflection, where will it go, depends on a rule. Which rule? The law of reflection, I equal to R. So what is I and R here? You have to draw a tangent here at any point. You draw a tangent, normal, I and R. So if you do this construction, you can actually prove it mathematically that whatever light ray starts from one of the foci of an ellipse will, after reflection, necessarily come back to the other ellipse. So we make use of this clever trick in cavity design of lasers such as ruby and whatever I am going to talk next. Solid state lasers, you can do it, make use of this conveniently, and what you get is a very powerful, very high efficiency, because you are not allowing any light to be lost. All the light beams necessarily go to do their purpose of exciting the ruby rod. Of course, it is a rather later development. Originally, it was like this, what you see here, the picture here. The ruby rod is kept here, and the flash lamp, just like some of the new lights that you see, CFL bulbs, something like that. It's not CFL, of course, it's a tube. So the ruby was covered by this, because at that time they thought this is the best design. Maximum amount of light goes into the rod. You can see from this diagram. So again I repeat, this purpose of the lamp is to excite ruby, and purpose of ruby is to emit the laser. So if the lamp has to be, your design has to be efficient, maximum amount of light should go onto the rod. So this, okay, this is good enough, better than just keeping a cylindrical tube, because the helical tube will give a lot of light. All the inner surface, all those beams will go into that, but the outer ones are all lost. Light beams coming from here, all are lost. That is why the new design is considered. So this is the ruby laser. These are the basics of a ruby laser, and this is a solid state laser, which is very convenient to use. Solid state laser is very stable, sturdy, convenient, as opposed to what we are going to see some other systems that we are going to see. We will go to another laser, which is an NT-arc laser. We can go through all this later. You don't worry about reading it all at once. The medium. First, what is the medium here? The medium is something like, it's called a precious stone. It's actually crystal, and its name is ND YAG. YAG is yttrium, aluminum, garnet. I have written here. yttrium, aluminum, garnet. Garnets are a class of precious stones. This is again a crystal where some of the atoms are, this is aluminum again, aluminum oxide, some form of aluminum oxide. So some of the aluminiums are replaced by, sorry, this is not purely aluminum oxide, this is yttrium aluminum oxide. So some of the aluminiums are already replaced by yttrium. Yttrium is a rare earth element. Yttrium aluminum garnet, this is called a garnet. And that crystal, we again replace some of them by neodymium. So there are two dopings here. One, starting with aluminum oxide, there is, of course, one doesn't have to start with aluminum oxide, it is already available in nature as garnet, but we can also grow it. For laser action, you will have to grow. So aluminum oxide, and then some of the atoms are replaced by yttrium, yttrium aluminum, garnet is the thing. And from that, we replace some of the atoms and make it Nd. So we put Nd into neodymium. Neodymium is a rarer thing into the lattice. Then again, the crystal field effect happens as in the case of ruby. Why do we do all that? Why do we have to look for this precious yttrium, aluminum, garnet and put neodymium? Then we get a very convenient laser level system. That's the whole purpose, to get conveniently to get the laser action and stimulated emission. That's the purpose of doing all that. So that gives you the specific kind of energy level system which we are going to see. That's a medium. That's a laser medium. Nd:YAG. This is solid state medium. We use optical pumping. This has broad bands, crystal field bands. We use optical pumping. The wavelength, we can have different wavelengths, but 1064 nanometer is the most common wavelength available. How do we get different wavelengths? Depending upon where we excite, which part of it which energy level set we excite, we will see in the diagram. So this can be, the very interesting thing about this is, this laser basically emits at 1064 nanometers, which is in the infrared. You know that there are only very specific wavelengths available, helium, neon, ruby, like there are very specific wavelengths available, not at any number you like. If you want a laser at 500 nanometer, there may not be any laser available at 500 nanometer as such. So this gives very strong, very stable and convenient emission at 1064 nanometer, which is infrared. You can't even see it. So what do you do with it? How do you get visible laser light out of it? That is where we use what is called second harmonic. Second harmonic generation or any harmonic generation is a nonlinear optical effect. It's a quantum mechanical process which is called a nonlinear optical process. It is like wave mixing. You might have done in some electronic circuits. Consider two waves, omega 1, frequency omega 1 and omega frequency omega 2, two oscillations of omega 1 and omega 2. In an electronic circuit, appropriately designed electronic circuit, you could mix the waves and get omega 1 plus omega 2 and omega 1 minus omega 2. That means the sideband frequencies you call it. Okay. So originally you start with omega 1 and omega 2, you get omega 1 plus omega 2 out of the system. This is called wave mixing, and this happens in nonlinear optical circuits, the systems, or electronic circuits also. In the case of optics, it is light we are talking about. In the other case, it is electric oscillations, that's all, of any frequency. Okay, so we have omega 1 and omega 2, we get omega 1 plus omega 2. Now put omega 1 is equal to omega 2. Then what do you get? You get 2 omega. Okay, so you give frequency omega and what you get is frequency 2 omega. This is called second harmonic generation. Similarly, using a nonlinear optical medium such as a KDP crystal or ADP crystal, there are several crystals like that. You can also get a third harmonic. You give frequency omega, you get 2 omega and 3 omega. 2 omega is called second harmonic, 3 omega is called third harmonic. What will be the wavelength? It will be half of this and 1/3 of this wavelength here, because the frequency is doubled and tripled. Thus, you can get 532 nanometer green in the green region and 335 nearly the violet, ultraviolet region. Both can be obtained from this laser system using the technique of harmonic generation. This is very important because Green is very important. Visible is important. Green is very important for eye surgery. So you would what you use for you might have heard in some hospital they use Nd:YAG laser for eye surgery. What they use is the 532 nanometer mostly. So each line has its own application in all the different applications. So the process here is, the physics here is that there is a harmonic generation which gives you second harmonic and third harmonic of the fundamental. 1064 nanometer is the fundamental, 532 is the second harmonic, 355 nanometer is the third harmonic. This is a 4-level laser system. It is very stable, very efficient, very convenient and very versatile. It can be used very easily. Very small ones or very big ones with the versatile, I mean small energy, large energy, all this is possible. Continuous systems are possible, pulse lasers are possible, all this is possible. It's so convenient that doctors can use it very conveniently in eye surgery and things like that. So this is the Nd:YAG laser. Now let us go to the next level and look at the energy level diagram of this. Here again a lot of quantum mechanical concepts are involved, but basically what you see is the splitting of energy levels. First of all, this set of energy levels will come only from this Nd:YAG, not from aluminum oxide or yttrium aluminum oxide garnet. You will only get if you put Nd:YAG. So this splitting, how it splits, what are the names, all involves some quantum mechanics which you are not aware of right now. Take any one of this. There is a band. There are closely lying energy levels here because it is a solid state system, crystalline system. So you have a band instead of a level. So any one of this can be excited, and from that some light is lost, some energy is lost as non-radiative, and then this is the third level and you get a fourth level here, and then you get laser action. Here again let us look at 1064. 1064 is the most commonly used Nd:YAG wavelength. This is the upper laser level and this is the lower laser level. Again, if only two levels are there, you cannot get population inversion. So here we do two tricks. We want more population here, less here. So we want to increase the population in the upper laser level. We want to decrease the population in the lower laser level. In a 4-level system, we do both of this. How do we do? We look at another energy level, arrange for another convenient energy level, pump it, optically pump it with a flash lamp, and then get the atoms to this level, to the upper level. So we populate the upper level artificially from using another method. So you have a large number in the excited level. Simultaneously, we do another clever trick. We take away the atoms from here. That naturally happens because it's an excited state and this is the ground state. Naturally, this will go away. It will de-excite. We choose such an energy level system which will de-excite very fast. So very quickly, how quickly? This is 10 power minus 12 and this is 10 power minus 8. Very quickly we populate the upper level and depopulate the lower level. In other words, we have to choose a system where this interaction happens very fast and this decay happens also very fast, and this is relatively slower. Then we have the trick of population inversion, achieving population inversion in this, between this and this. Similarly for another set, any other set. For a given laser phenomena excited, for a given laser emission, you have only 4 levels. So if you use some other wavelength, that's also shown in this picture. That is an Nd:YAG laser, a most common laser, especially in scientific applications and medical applications. The cavity design is again important. If you see a picture of the cavity, so far I have been talking about. So now you have there are different designs. This is not the elliptical design, some other design. There are 2 flash lamps on either side of the crystal in the cavity. This is the mirror system. Okay, you can use either system, anyone, whichever is best and convenient. You can use either this way or helix or ellipse. Make use of the property of the ellipse. So this is, by the way, the end mirrors are not exactly parallel always. There are a lot of research and a lot of results have come out on what kind of mirrors to use. And that is a matter of detail, but the purpose of that is to provide the feedback. When you consider the laser as an oscillator, the feedback is provided by the mirror system. That is the importance of the cavity design. I mentioned sometime in the first lecture that laser is an amplifier laser is also an oscillator from the electronics analogy. When you say laser is an oscillator, oscillators need feedback. Where is the feedback coming from? It is a mirror system and mirrors of the cavity which provide the feedback from in the language of electronics, so that it becomes an oscillator. Now the popular laser, helium neon laser. I am taking helium neon laser later because I clubbed the two lasers together. I want you to see the sequence. First I talked about ruby laser, which is a solid state laser with optical pumping, which was a 3-level laser. Then I went to the Nd:YAG laser, whose principle is very similar in the sense both are replacing some ions in a crystal, both work on that basis, and in other words, in the technical language, it is a crystal field effect. The energy levels arise from crystal fields, and then both are solid state lasers, convenient lasers. One is a 3-level laser and the other is a 4-level laser. So you can look at it, go back to what I discussed about the 3 levels and 4 levels, and then you will get a complete picture of that. So that is one set. Now we talk about the helium neon laser, which is very popular and very old. Helium neon laser is very convenient and cheap. Continuous wave oscillation is possible. This is again a 4-level laser. It is a gas laser. So basically we have a gas tube consisting of helium and neon. Why helium and why neon? That is important. We will see that.